I want to talk to you about our perspective on Cloud SDN from Alcatel-Lucent. And to start, really, I want to set up the challenges that we're seeing in the industry, in particular for network operators. What's happened over the last 10, 15 years is we've had several key changes to infrastructure that is really driving this cloud enablement and creating the cloud as really the infrastructure architecture going forward that we're going to be using. The first thing that happened that enabled this concept, and today we expect everything to be available on the cloud. Part of that came from the migration onto IP. All services are on IP, your smartphones are on IP, your laptops are on IP. Everything is now converged onto the IP network. It has become the common fabric on which we offer services. So that's one very key aspect. It now enables us to put functionality into the IP network wherever we like, knowing you can reach it from whatever device you happen to be on. And that's really what the cloud is. The second thing that's happened is the access network build out. We estimate there's something on the order of, in North America alone, $250 billion have been spent since 2000 building out the access network. That's the cable infrastructure, fiber infrastructure, copper infrastructure, all the aggregation networks that go with that. And that investment is what makes the cloud reachable. So not only do we have these devices and a common IP fabric, we've got the bandwidth in place so that we can really start thinking about running applications in the cloud and having access to them from anywhere. And really the third piece is what's happened with compute and virtualization and the idea of these huge data centers that have virtually infinite compute resources, where really the sky's the limit on what we can do with that compute capability. And that's really enabled a whole new, entirely new business models, entirely new types of applications, everything from how you buy your supplies for your home, perhaps from Amazon, to how you consume video on demand, streaming it from the cloud over your broadband internet connection. So all of these things have sort of combined to create the cloud infrastructure as we know it and begin moving applications to the cloud. However, it's not that simple. If we go back in time a bit, if I set my Wayback Machine, as Jeff says, set it back maybe 30 years, we were very busy going to centralized architectures then, the concept of mainframe computers. And why did we do that? It was driven by economics, and I believe today it's still driven by economics. Computers were very expensive, so you really couldn't have one locally. So we built these mainframes. We had terminals to access the mainframes. Terminals were cheap, computers were expensive, and that really was what created the need for a network in the first place. Then along come the 90s, suddenly there's these personal computers that have a lot of capability, and we shifted the opposite direction. We moved everything now was running on the desktop, enter Microsoft Office, new types of applications that ran on the desktop. We've now reached a point where we have this cloud infrastructure that has potentially enormous capacity, but we also have in our pockets, most of us, these devices that have a lot of compute capacity, with us, whether it's a tablet or a laptop. So it's not so simple anymore. Is it centralized? Is it distributed? Well, the answer is it depends. It depends on the application and the economics of whether you want to centralize it for economic reasons or to access more compute or more storage, or whether you want to distribute it to make it run fast, have low latency, be available whether or not the network is there. All of this has significant implications on the network. The network has to support all of this. So we can't say that we understand the exact workloads because they're shifting constantly. Between the data centers, from the data centers to the end users, it's becoming increasingly unpredictable how the traffic needs to flow. To respond to that, we really have to rethink how we build networks. And this is what a lot of what SDN is all about, is that rethinking process. We know we need to make them more agile. We need to leverage some of these capabilities. The fact that these virtualized cloud infrastructure exists, how do we take advantage of that to build more agile networks? That's what SDN and NFV are all about, is taking advantage of that compute infrastructure to put in more powerful control systems, more flexible control systems to control the network, and even potentially virtualizing some of the network functions themselves and running them on that compute footprint. At the same time, though, we still need the network fabric. It's not gone. You still have to move the bits from point A to point B, so that's still there. It may be SDN controlled increasingly. Some functions may be pulled out of it and run in the cloud, but the fabric still has to be there. And so the challenge really is, how do we tie these pieces together to build that elastic, adaptable network? This is a high-level diagram of SDN. And SDN is more than carrier SDN, which we've talked a lot about today. It really started in the data center, responding to the challenge we faced as we began to virtualize compute. So with every VM, there's a requirement for network connectivity. And when you go from one IP interface per server to potentially tens, hundreds, or thousands of IP interfaces per servers, you've got to manage all that connectivity. And when those VMs are coming and going and moving around and constantly changing, created a huge, huge problem. And we've just now really started to apply SDN technology in the data center to do virtualized network automation. So that was the first real piece. We're starting to have those systems deployed. However, we need the physical infrastructure, which ultimately gets traffic to, from, and in between those data centers, to also be dynamically controlled. So ultimately, what we want is a common control layer driven by very simple policies that controls both the physical network as well as the virtualized network that runs within the data centers and ties all that together. And the approach here, by the way, isn't one giant controller in the sky. We look at that and say, wait, we can separate the problem and use federation, different kinds of controllers for different tasks, bring them together via common protocols and interfaces so we can tie all this together. And an interesting point here is that doesn't mean the underlying network fabric doesn't have full functionality. There's still going to be a fair amount of complexity in that fabric. The key is that we abstract that complexity. So we don't expose it to the services, and we define the services with very high-level languages via directory, via policies. And I'll talk a bit more about that. So what's required for that carrier SDN piece, the piece that controls the physical network infrastructure and dictates how traffic's going to flow through that fabric? Well, the first thing we see there is it has to be multi-dimensional. So you can't have an SDN that only understands layer 0 or only understands layer 1 or layer 2 or layer 3. It really needs to peer across those layers. And we talked about that a bit earlier in the IP optical discussion. There's very significant optimizations we can gain if you can go across layers. You actually understand how the capacity is being used and can build very optimal network infrastructure. The other key point is it must be multi-vendor. Right? We really can't, we would like it to be all Alcatel-Lucent. That would be fantastic. If you're buying from us, you should buy it all from us. But we heard from the gentleman earlier that that's not realistic. And you need the flexibility to mix and match, put in the right vendors for the right parts of the infrastructure. So it's got to be multi-vendor. So multi-dimensional across those three attributes, multiple layer, physical and virtual, as well as multi-vendor. The other two key pieces of this is we need intelligent network control, but we need that intelligent network control to be service aware. So we can tie those two together. Likewise, we need to have smart service delivery. The point of this is to deploy and enable services, but the service delivery has to be network aware. So you need to understand how enabling a service will impact the underlying resources and vice versa. So those pieces really need to come together. And we need all of this to happen in a, you could say, real-time or online fashion. It has to be watching the network at all times and responding to service needs, because the goal here is we want on-demand services that can react at the rate at which the applications are changing in the cloud infrastructure. So the network is adapting itself to meet those needs at all times. And it's got to be simple, and it must be automated. I think somebody mentioned earlier this notion of machine to machine. And when you think of machine to machine, you probably think typically about collecting up data from smart meters and that sort of thing. But the reality is that the highest traffic volume today is going between data centers, and that's all going between servers. There's no humans involved in that process. It's a workload that, yes, a human at some point has triggered, but when it runs, it expects a lot of network capacity, and those are machines that are driving that capacity, not humans. So it's got to be automated. It has to have software programmability so it can respond to the applications. The challenge today, if we try to solve that problem and make an automated network, is the way that we've built networks and the way that we expose the network infrastructure to the orchestration or the OSS or whatever you want to call that top layer. You know, what we've typically done is each vendor comes along, we've got our great boxes, we may have a network management platform or some software that at least can take the portions of the network we build, collect that together, but we've tended to expose pretty detailed interfaces up to the OSS that get down into the pretty low levels of how all these different devices operate, and sort of throw the problem up to the OSS layer to figure out how do you integrate this on an end-to-end basis to create a service. So the complexity from the network was not abstracted, it was exposed directly into the OSS layer, and so we end up with these big, complex systems that try to tie together all these different types of devices, and they're literally speaking into command line interfaces, pretty low-level interfaces to control the network elements, and that simply won't do. If we want these networks to be automated, we've got to change the architecture. This is what SDN, carrier SDN, is fundamentally about. It's about inserting a software layer in between the OSS or orchestration infrastructure or the applications that ultimately abstracts away the complexity in the network and presents higher level objects and services, object models and services to the higher layers. So if you're an application and you want capacity, you don't need to understand the ins and outs of how all the devices work. All you need to understand is I need 10 gigabits from this location to that location, 5 gigabits to that location, and I want them fully meshed. Very simple high-level constructs. And it's the SDN layer's responsibility to take those simple constructs and adapt it to the actual network elements, understanding the specific configuration capabilities, push all that configuration into the network elements. So that's a real key piece, is that the network is abstracted by the SDN layer, simplified. The other key piece is we want the flexibility to create new services. So we want all of the services to be defined by simple high-level policies, policies that describe how things connect, who's allowed to connect to what kind of capacity should those connections entail. Very simple constructs that allow you to define services. An example of this is service chaining. Right? You want service chaining. So I've got a customer access port that I want to connect to the internet, but I want it to go via a firewall and a parental control system. So you describe that service at a high level. The SDN controller then maps that to all of the underlying technology required to stitch all of that together and ultimately deliver the service. And so we've sort of pushed the complexity down. And to be honest, what's happening with a lot of the initiatives in the industry is we're even simplifying those interfaces on the devices. So moving from CLI interfaces to NetConf interfaces, moving to higher level Yang models on the device itself, so that even some of the complexity inside the device is abstracted away to the SDN controller. So that begs the question, well, what can I do with this? And what are the near-term capabilities that you can drive from this? And I'll separate it into two categories. This slide really looks at the internal network infrastructure and what are some of the things we can do to run the network much more efficiently. In the next slide, I'll talk about some new services that we can enable once we have this infrastructure in place. So I actually talked this morning about resiliency, and it was in context of IP and optical, and if we can interconnect those two layers from a control perspective, we can get much better resiliency. We can go even a step further with SDN control. A lot of the resiliency schemes that we implement in the network today, they're done on a nodal basis. So every node has its own view of the network, and it's determining its own schemes for, if I see a failure, how do I reroute? Those can become inefficient because there's no node in the network that actually sees the global picture. So a failure, 4 hops away that may impact it, it may not make the right decisions. By centralizing the control in the SDN layer, you've got a system now that can look across the entire network and can do very sophisticated resiliency schemes. So look at complex failure schemes. If this link fails, what services are affected, and determine the return paths or the resilient paths for all of those services in a very sophisticated way. Literally looking service by service, mapping all of that out using complex algorithms. Very difficult to do unless you have this centralized control infrastructure. Another capability of having this system operate online in real time is responding to service demands and potentially reconfiguring the network to meet that service requirement. So we show a simple example here where a new service request is entered into the network, requires 10 gigabits per second from point A to point B. There's multiple paths through the network, but none of the paths perhaps have 10 gigs available. So now you have a choice. You could just deny the service request. However, with the SDN control layer in place, we can recognize that, well, there is actually enough capacity. It may be spread across multiple links. If we can consolidate some other services, we might be able to free enough capacity for the new service request. So simple example, relocating a 2 gig service onto another link, freeing up enough capacity to then admit the new 10 gig connection. So a simple example. The real idea here is what we're doing is it's bandwidth defragmentation. And in this case, as I described, we're looking at the requested load of the service, which, by the way, may be very different from the offered load of the service. So if you're a service provider and you're off selling e-pipes or VPN services, there's a bandwidth configured on that e-pipe on the VPN service, but we all know that the actual customers aren't using all that bandwidth all the time. That sort of represents their peak, which leads to the third example. And this is a technique to begin to really optimize the network load. A few years ago, Google made a big splash in the industry, particularly in the SDN space, by announcing and talking a bit about their SDN architecture they were using on their core, which allowed them to drive their link utilization up into the 90% range while maintaining full resiliency and being able to recover from failures. They actually published a paper that talks about how they did this. There are really two key things that they had to their advantage that network operators do not have. And the first is that they control the workloads, because it's their compute infrastructure. They control when those jobs run, where they run, and they know how much network capacity they need, which allows them to effectively time shift their workloads, which is one big advantage they're getting. The second is that they have a relatively small number of sites. I think they mentioned something like 12 sites in their network, which any network operator in the room, particularly if you have access network, you've got way more than 12 sites, or your networks are far more diverse. So the challenge, if you're a network operator and you want to get to that level of utilization or really push the network beyond the 40, 50% that we're used to, how do you do that when you don't control the workloads and you have many, many sites, much more complex topology? And so this is what we believe we can solve with an SDN, carrier SDN, using the analytics capability. So part of what the carrier SDN is doing is it has real-time visibility into how traffic is flowing in the network. And as we said, if it's doing the right thing, it's not only network aware, it doesn't just see the pipes and how heavily utilized the pipes are, but it's also service aware. So it actually can begin to understand the duty cycles of all the services flowing across those pipes, and you can begin to think about, can the network be slightly reconfigured from time to time squeeze out a bit more capacity once you've characterized those duty cycles? So this becomes more of it's a traffic engineering. It's a combination of offline and online, but really using analytics to understand the duty cycles and remap out the network topology. And using these techniques, we can squeeze a lot more capacity out of the network. Now, to really get good, we need to control the workloads and when they run. And a lot of folks today have talked about bandwidth on demand. And I've talked to a lot of network operators about bandwidth on demand. I've talked to a lot of enterprise customers about bandwidth on demand. They both want it, but for diametrically opposed reasons. When you speak to the customer of bandwidth on demand, why do they want it? Well, because they have a backup that requires so much capacity and it only takes 3 hours to run. And they don't want to buy that pipe for 24 hours a day to use it 3 hours. They're looking at their duty cycle saying, wow, I'm spending way too much money. If I could buy it on demand, I'd spend way less money. The network operator is the opposite. What they're doing is looking at that saying, I've sold them this capacity, and I know they're not using it all the time. Boy, I'd really like to resell that capacity, but I can't really predict if and when they're going to use it. So if I try to resell it, I could end up leaving myself exposed and not meet the SLAs. So if you want to solve this problem, this is where, with an SDN, you can start to do sophisticated things like bandwidth calendaring. And several people mentioned this earlier today. I really think of bandwidth calendaring as a way for network operators to start to influence the workloads on their network. And this is basically by selling futures contracts and begin to price in their capacity, sell it in the future. They now have very good visibility and can start to really optimize the network because you have some idea when those workloads are going to run, how much capacity they're going to use, and ultimately drive, maybe not all the way into the 90 percentile range that a Google or Facebook or others may have when they only serve one master, which is their internal development team, but certainly driving capacity up much, much more than we do today, getting more revenue across the network while offering a valuable service to the customers, which is ultimately a lower cost for them. So that's it. Thank you very much. You can see here, this sums it all up. I'm not sure where that diagram came from for a marketing team, but there you go. It's a cloud in a circle.